How does polynomial regression fit nonlinear data? Imagine trying to draw a smooth curve through a set of points that don't line up in a straight line. That's where polynomial regression comes into play. It's a way for machines to understand complex patterns in data that aren't just simple straight lines. In supervised learning, the goal is to teach a computer to predict outcomes based on input data. Regression algorithms help with this by finding the best way to connect the dots. When the data follows a curved or wavy pattern, simple straight-line models won't do the job. That's when polynomial regression becomes useful. Polynomial regression works by transforming the original input features into new features that are powers of the original ones. For example, if you have one feature called x, the model adds squared, x cubed, and so on. These new features allow the model to fit a curve rather than a straight line. Think of it like adding more bends to a line to better match the shape of the data. The model then uses these expanded features to find the best coefficients that fit the data. It's still called a linear regression because it's linear in the coefficients, but the relationship between the original input and the output can be highly nonlinear. For example, a second-degree polynomial can model a single curve, while a degree polynomial can fit to bends. Choosing the right degree of the polynomial is important. Too low, and the model won't capture the true pattern. Too high, and it might start fitting noise instead of the real trend. This is called overfitting. Tools like Python's scikit-learn make it easy to implement polynomial regression by transforming features and then applying linear regression. You'll see polynomial regression used in physics to model projectile motion, in biology to study growth rates, and in economics to analyze nonlinear trends. It helps machines understand data that curves and bends, which is common in real-world situations. Understanding how polynomial regression fits nonlinear data also helps us see how AI systems learn from complex patterns. But it's important to remember that more complex models can sometimes be less reliable on new data. Overfitting can make the model perform well on training data but poorly on unseen data. That's why choosing the right degree and understanding the data are key. In the end, polynomial regression extends the simple idea of drawing a line to fitting a curve. It's a handy tool for modeling nonlinear relationships in supervised learning, making it easier for machines to learn from data that doesn't follow a straight path. This understanding is fundamental in how AI systems analyze and predict real-world phenomena.